All right. Good morning, ladies and gentlemen. Welcome back to your favorite class. Rawr! And what is now, I think, week 5? I think. What week is it? What year is it? Week 5, right? Or is it week 4? Because we missed a week. I don't know. What year is it? Okay, I don't know. Right. So welcome back. Hopefully y'all were able. Yeah, Dan Scully replied. He probably said something like, yeah, what year is it? Who knows? 4, I think. Okay, yeah, who knows? 4 out of 11, even though we missed one, so it's really 10. So we don't have finals week, so who knows? Okay. So, right. Hopefully you guys got your homeworks in. Homework 2, a little bit more computationally intensive. So hopefully we, brushed off those MATLAB skills, got those functions right. And yeah, because I promise you're going to use those functions again. All right. And we're going to use them for your next homework. Okay. Which will be homework number 3, which will be on material that we're going to dive in on starting today. And that material is hygrothermal strains. Yes, that's not a spelling error. Hygro is what I really mean. Okay. It's like, do you mean hydro? Like kind of, but not really. Okay. Hygro. All right. So the homework number 3 is going to be on hygrothermal stresses and strains. And I'm putting it together right now. Kind of putting the last touches on it right now. I couldn't quite finish it yesterday. But you'll probably see that sometime later today. And that'll be due a week from today, which is Monday. All right. Other announcements for the class. Homework 3 is due on the 13th. Yeah, it'll be due 1 week from today in theory. But you know the difference between theory and practice. They're the same in theory, but not in practice. Okay. So yeah, homework 3 due on the 13th. And you have scheduled your first exam next Friday. Now, if you've noticed kind of the calendar and the pace that we've been going along, we're a little slow. So I've cut back a little bit on the hygrothermal notes, and we're only going to talk about it for 2 days. And unfortunately, I didn't know that this upcoming Friday was also a holiday. So the 10th is actually a kind of a holiday. So we're not going to have lecture on the 10th, which is this Friday, which is another kind of disappointing discovery. I don't remember that being a holiday in the past, but I'm also going crazy in isolation, so who knows. So anyway, no class this Friday. Homework number 3 will be due Monday, and it's only it's a little bit of a shorter problem than the one that you just had, than the homework that you just had. Okay. Any other questions? I think that's probably about it for announcements for the class. I will be back in 1 second. Okay. All right. Well, if there's no further questions, I did upload a new set of notes to Blackboard on hygrothermal stresses. And I kind of want to start there today because there's some kind of cool pictures that sort of introduce the topic and outline why I think it's important. Okay. So I'm going to flip over here and kind of show you guys some of the PowerPoint slides. All right. Sam, glad you got your homework in. Good job. Whoa. Okay. So the new topic that we're going to dive in on is hygrothermal and residual manufacturing stresses. So if you remember back in week number 1, actual week number 1, our second and what turned to be our last final in-person meeting, we created this composite here. Okay. So can you guys see my camera? Do I need to turn my camera on? Can you see my camera? Or not? Question. I just want to make sure I'm not like holding. I mean, it's tiny in the lower right, I guess. But okay, good. All right, so this composite is a composite we manufactured, and remember, it had this like residual curvature. So if you can kind of see this, it's got sort of this like curvature that's sort of like pointing in this direction, and we have this like residual curvature to this piece. Okay, there's also probably residual strains that are sort of longitudinal that we can't really interpret because we didn't really know the original size of the piece. Okay, so what we're going to talk about over the next couple of days is the math behind how those strains and those curvatures develop, given the manufacturing temperature changes or what might be moisture changes inside the piece. So that's where kind of this word hygrothermal comes from. Hygro meaning moisture absorption and thermal meaning thermal. All right. So changes in temperature causing sort of shifts in the piece. Okay, so the first thing that I want to start with is kind of like a thought experiment on coefficients of thermal expansion when you have two different materials. And hopefully you've all sort of seen something like this before, but I'll just start here. Okay, so let's have a thought experiment where we're considering two materials with different coefficients of thermal expansion. And let's think about like a glass and epoxy composite, like a very common composite that's made. We would have the coefficient of thermal expansion for glass being some random value I found here, about 4 micrometers per meter degree C, meaning for every 1 degree Celsius that I heat this thing up, it expands 4 micrometers per meter. Okay, so that's kind of like a thermal strain. And for the epoxy, we have a significantly higher coefficient of thermal expansion. So for every 1 degree C that I heat this thing, it expands 50 micrometers per every meter of length. All right, so that's the general idea. If you consider manufacturing a composite at high temperature, it becomes solidified in sort of this high temperature state. Okay, so when we fabricate a composite, we fabricate it at temperature, let's say 150 degrees Celsius. All right, the resin is in its liquid state at that high temperature and solidifies at that temperature. So the piece is kind of like thermally neutral in terms of stresses and strains at that high temperature. Okay, so that's its healthy configuration, or its configuration with no internal stresses and strains. So what you may think about then is, as you cool that down from manufacture, okay, so here's our condition of manufacture. If I were to cool this down and there was no bonding between the glass and the epoxy would shrink more than the glass would shrink. Okay, and that's just because of this higher coefficient of thermal expansion. However, we know that there is bonding that exists between the epoxy and the glass. And so what happens is there's this kind of like compromise where the glass shrinks more than it wants to, and the epoxy doesn't get to shrink as much as it wants to, especially at that particular interface. So this is the general idea there. Okay, so this is a very like crude model of what's happening or what's going on, and so you get sort of like this pinching that happens where you sort of form this like trapezoidal shape, but in actuality what happens is they kind of curve against each other, something that looks like this, which is very reminiscent of what you see with this particular laminate, where you have this sort of curvature that's occurring in this particular laminate. All right, so there's one side that's attempting to sort of like contract more during the cooling than the other side, which doesn't necessarily have to contract as much. Okay, so we're going to talk about how that curvature and how that math tends to work for our laminates, right? That may have many different layers, which in of themselves have different coefficients of thermal expansion in different directions. Also, the materials that make up those lamina, carbon fibers, may also have different coefficients of thermal expansions in different directions. A single fiber itself. Complicated, man. So all of these things sort of contribute to like these residual strains and curvatures that might happen inside of a laminate from the cool down process, because it's sort of unstressed and unstrained state is this high temperature in which we fabricated the piece. Okay, so let's see some cool pictures of this in actual reality. So in practice, these are some pictures that I took, but the idea here is that let's say that we had some orientation that looked like this of glass and epoxy, and it was solidified in this sort of configuration, which would be like the hot manufacturing condition. Okay, so this is its sort of like nominal state. So when we cool it down, this sort of like pinching wants to happen. Okay, like the epoxy is trying to like pinch in, and the glass is trying to resist that additional pinching. And in very extreme cases, what you see by this picture here, for instance, I'll blow it up a little so you guys can see it a little bit better. I don't know how good the feed comes through with your guys' resolution. I think like the resolution on your screen is not quite as good as what I see on my screen, just because of bandwidth issues. So I'll blow this up. And the basic idea here is that we have a series of glass fibers. Hopefully you can see them. They're kind of coming out of the paper here for this particular composite. And then we have a series of glass fibers that are kind of coming down this direction, and they're kind of across the plane. But the basic idea is that the arrangement looks something like this, where we have a glass heavy region, and an epoxy heavy region. So you see this sort of black region here, that's pure epoxy. And so this is a composite that has cooled down from high temperature, and this sort of like pulling is occurring. And this case is particularly severe because in this case, the pulling was so severe that there was actually fracture that occurred. So those of you taking Schaefer's fracture and fatigue class know that there has to be some sort of nucleation or some sort of initiation point for these cracks to occur. So there was some nucleation point in this particular piece, and the stresses that were sort of caused by this coefficient of thermal expansion mismatch that sort of like pulled this material apart was actually so great that it actually created a fracture, right? And that's because you've got all this internal strain between these two components that kind of leads to this really stressed condition where we're actually trying to like force away this particular material. Okay, so this is a generally severe example where the thermal stresses that were developed were relieved via this fracture. Okay, so if that fracture wasn't there, it would still be under a significant amount of stress and strain. But now with that fracture there, you sort of like relieved that tension or relieved that energy. Okay, so what we're going to talk about is not the fracture, because fracture itself is a really complicated topic and a lot more depth to the theory. But less severe examples than this can create distortions and warpage, which are still an issue. Okay, so like we see here. Okay, this laminate probably doesn't have a lot of internal fractures like the one that you see in that picture there, but you can see that this warpage still exists and could potentially be a problem. So if you're anticipating a certain geometry for your piece that needs to fit in a certain slot or needs to, you know, two pieces or two ends of the piece need to be bolted together, like it could be pretty problematic if you have all this like warpage going on or shrinkage that you don't anticipate. Okay, so that's mostly what we're going to talk about. But to kind of round out this discussion about the fracture of this glass epoxy composite, I just want to show that, okay, here we have again a larger view of this composite with the fracture inside of it. So here is the fracture on this particular composite that has occurred while the sample was cooled. And this particular sample was cured up to a maximum temperature of 177 degrees C. So pretty high temperature cure for this particular epoxy composite system. All right. So this was a problem that I faced in graduate school, and I was working on a three-dimensional composite. If you notice, this is a three-dimensional composite because it has this fabric glass toe, which kind of like runs through the thickness. So this is a three-dimensional composite, and at that time, three-dimensional composites weren't really that well understood. So a lot of manufacturing processes for 3D composites were still relatively new, and it's kind of a new field. It's the Wild West. Pew, 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 pew. All right. So I had to sort of adapt on the fly and say that, okay, if the temperature change for this cure from 177 at room temperature is about 150 C, let's see if we can reduce the total temperature change required from the heated condition to the cooled condition by changing the cure schedule. So instead of a maximum curing temperature of 177, I just reduced the cure temperature to a maximum of 121, which is 250 F, if you're wondering why the number is weird. 8 hours at 121 C. So now the maximum temperature change inside this piece from its heated condition or nominal condition to its room temperature condition is only 95 C. All right. So this eliminates about 1/3 of the strain inside of the piece that comes from this coefficient of thermal expansion mismatch between the individual pieces. Okay, so generally then with a lower temperature cure, the overall temperature change during cool to room temperature was less, reducing the stress between the glass and the epoxy. All right, so that's kind of the idea there behind what was going on with this particular piece. Now, that again is an extreme example where you sort of have fracture occurring because the stresses are so great that they're creating internal fractures during the cooling process. All right, here are some other examples as well. So if you have the deck in front of you, you can maybe see this a little bit more clearly. But here are some other examples. This is a metal shape memory alloy wire. So if you guys have ever seen shape memory alloys, like nickel titanium is a common one. This is a nickel titanium wire inside of an epoxy matrix. And there you have pretty substantial coefficient of thermal expansion mismatches. So between a metal and, let's say, a carbon fiber, like those coefficient of thermal expansion mismatches are tremendous. So in this particular image, you see a lot of stress cracking that's occurring around like the radial portion of this particular wire. And that's because this guy is trying to contract significantly more than the surrounding material as it's cooled from its high temperature cure condition. Okay, so it's trying to contract around what would be sort of a bonded surface. All right, but that's kind of very intense, very severe, this like fracture that occurs. What we're going to talk about is more about like distortions and warpage, which might occur during the cool down of the fabrication of a laminate. So I particularly like this image quite a bit. And this is an image from my former PhD advisor who took this image and made these composites, right? So here is a series of composites that look a lot like the one that we tried to fabricate, all right? So what you'll see here, these are stacking sequences, 0, 2, 92, the T. T means total, so like not symmetric. So this is a 4-layer composite, 2 layers of 0, 2 layers of 90. And you see it has this very curved sort of flavor to it. I mean, it looks a lot like this, which is the composite that we made. Okay, so it has a lot of like residual curvature. Similarly, here's a 0494. You can see a lot of curvature. Here's a 0294. You see a lot of curvature, and a series of others, right? A 0298. You see this is very, very curved. So we see a lot of. This one's kind of cool. This plus minus 45 composite that has sort of like this torque warping that's going on to it, right? Sort of this like this torquage to it. So, anyways, you see a lot of these different composites showing residual curvatures and strains that you may want to avoid if you're going to manufacture composites. Down here, this is also an interesting one too. This is a nylon reinforced glass fiber. I don't know what you want to call this, but a basin. I don't know. This thing was injection molded, and there's 2 injection molding conditions here. So the resin is a fiber reinforced, short fiber reinforced nylon. All right. So injection mold your short fiber reinforced nylon. If you don't have enough pressure, what happens is you get a piece that looks like this. Okay. Because of not enough pressure, there's some alignment to the fibers as they're injected into the piece. So if you can imagine them sort of like shooting into the mold that is the injection molded piece, they sort of like move in, and the fibers sort of like align themselves and hold themselves in a certain alignment, creating a very like orthotropic material. So when it cools down, there's this change of or different coefficients of thermal expansion in different directions, and it results in non-uniform shrinkage in the different directions, which creates this warpage. Okay. So to modify, they kind of changed the injection molding pressure, and now this is your what the piece should actually look like given proper conditioning. Okay. So how are we doing in the world out there? People awake? Got their coffee going? I got orange juice today. I'm trying to like load up on vitamin C. Okay. I'm doing a little better with the trying to avoid coffee, I guess. All right. So I'm now going to sort of switch gears and go to the writing pad kind of for the remainder of the notes here. It's probably going to take us 2 or so days to get through the notes. So I'm hopefully not going to have to trickle anything into Friday. Okay. So let's now share the writing pad. And I hope you guys liked my little cat meme this morning. I'm going to try to like lighten things up a little bit and maybe have a different meme every day. I got a big stockpile. Don't worry. I know you've seen my door. You know, I have memes. Okay. All right, so the topic for today is going to be hygrothermal stresses. All right, so let's kind of give ourselves a general problem statement. So I've sort of like alluded to these things informally, but let's kind of formally talk about things that could contribute to shrinkage, warpage, so on and so forth if we have a composite that we're manufacturing. Okay, so general statement. We'll say here that since composites are comprised of multiple materials, with multiple different material properties. We can have residual stresses and strains that develop from a variety of factors. You can develop residual stresses and strains from a variety of factors. Okay, I've kind of talked about like thermal factors up until now, but there are others. And we're actually going to focus on thermal factors, but let's talk about some of the big other ones that you might see. Okay, so first obviously is what we've talked about so far, and that's thermal expansion. Mismatch, or coefficient of thermal expansion mismatch. You could have some chemical shrinkage that occurs or absorption mismatches. All right, so there could be chemical shrinkage. Or what I'll say is like some chemical absorption. So an analogy I might want to make here is like if I had a very dry t-shirt, it would have a certain size to it. And then if that t-shirt absorbed moisture, it would expand in size. Okay, so that's kind of a moisture absorption or a chemical absorption. You can have stresses that occur from non-uniform temperature distribution during the cure. And I want to ask a question in the chat. I want to get some answers here because I'm just curious. Did you guys ever talk about the Biot number in your heat transfer classes? So Biot number. Okay. Yes. 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 Okay. So you did talk about the Biot number. All right. So I'm going to kind of like draw a picture here that sort of explains what I mean by thermal gradients inside of the piece related to Biot number. So the Biot number, it's a non-dimensional quantity, Bi, which relates the conduction and convection inside of a piece, right? So what do I mean by that? Okay. Well, let's just get the definition down here. HL on K, where, okay, if we think about laminate that's being cured, okay, we talk about cure temperature like the temperature of the oven is the temperature of the piece, okay? That's not really the situation, okay? So if I put something that's cold into the oven, it doesn't just magically have that temperature, okay? It takes time for that piece or that thing that you're cooking to get that temperature fully into the entire piece, okay? So if we've got this composite, right, that's at room temperature, all right, so we're at room temperature, and suddenly we go to a temperature of, I don't know, 100 degrees C. Okay, so this guy starts at room temperature, and then all of a sudden your outer temperature, which is T infinity, is 100 degrees C. Okay, well, if that's the condition, immediately when you plunge this composite into an environment that's 100 degrees C, all the surface on that particular piece is going to reach that temperature. Okay, so we can approximate and say that at times T0, this temperature on the surface is approximately equal to 100 degrees C. But it's going to take some time for the inside of that piece to reach temperature. Okay, so this is at T equals 0. Basically, that temperature immediately becomes 100 degrees C on that surface. It's a good approximation. Okay, but inside here, T equals question mark. Okay. So inside of the piece, it takes time for this thing to heat up. Okay. And so what can happen is if you have a very high Biot number, this is a bit of a tangent, but we're all trying to learn here, right? If you have a high Biot number, what happens is that your convection dominates over your conduction, meaning that you have very high temperature on the surface and very low temperature inside of the piece because your conduction is very, very low relative to the convection outside. Okay, so with a high Biot number, your temperature distribution, here we're at T equals 100 degrees C, and it takes a very long time for the center to heat up. So what happens is, here we have T100C, 100C, and here we have T is approximately equal to room temperature, and this is for a long time. All right. So what happens is you get some distribution of temperature that's like 100 degrees C at the surface and room temperature on the inside. And because of this gradient of temperature, which might be very, if we sort of like drew this is like very hot temperature and this is very cold temperature, sort of like graphically, you would see that there is a lot of temperature difference even within the piece. Okay, and so within the piece, if you have these temperature differences and differences in coefficients of thermal expansion of the different materials, oh, gross. That's nasty. I don't like that at all. All right, you get all these complicated problems that happen. All right, if the Biot number is low, then it doesn't take very long for the center of the piece to reach the same temperature as the outside of the piece. All right, short time, let's say, I don't know, it depends on the material properties, but a couple of non-dimensionalized time units. All right, so it happens very, very quickly. All right, so the Biot number can really affect things of your particular piece. And the Biot number for the piece is complicated in composites because you have different materials with different, conductivities. So glass is not very conductive, but carbon fibers are conductive. So generally the carbon fibers don't suffer from this like thermal gradient problem as much as glass composites do. Okay, but anyways, that was kind of a side tangent. All right, other things that can affect can be affected by material transformations. Okay, so let's say we've got a metal matrix composite, and during cool we go from we transform into perlite instead of martensite. Okay, or you have some metal phase that you're not expecting inside of your piece because of thermal gradients and so on and so forth. And so if you end up with, let's say, a eutectic material here and a non-eutectic material over there, it's going to be a complicated situation where they have different structures and you have all these thermal, these stresses that occur because of transitions of the material inside of the piece. Okay, so material transformations, this is particularly true for metal matrix composites. All right. Plasticity can be a factor. This is particularly an issue for thermoplastic matrix materials. All right, and that's because plasticity is more rampant with thermoplastics than it is with epoxy, let's say, which is the thermal set material, and is much more brittle. All right, so plasticity for thermoplastic composites, and there are other things. There are other things that may contribute. Okay, we're not really going to chat much about those. Okay, what I'll say after sort of making this list is that we will focus on the thermal expansion and moisture expansion coefficients. Thermal expansion and moisture expansion in this class. All right. So if we want to have proper vocabulary or talk about this correctly, we would say in words. So proper vocabulary. So you can sound smart on all those job interviews you're going on, right? Proper vocabulary, we would say that we're discussing hygrothermal stresses and strains. Stresses/strains. Okay, so there's your proper vocabulary. Hygro meaning moisture absorption, thermal meaning thermal, stresses and strains which develop. Okay, so like I said, our focus, our focus will be on sort of the warpage and the strains that develop. And these develop from what I'll say minor temperature changes or minor material mismatches. Okay, so I would kind of classify stresses and strains that develop inside of a composite because of these thermal expansions as relatively minor or major. Minor ones would be ones that sort of just like give curvature like this, yet generally keep the laminate intact. Major ones would be like stresses that are so severe that they're causing cracks, they're causing fracture, all these sorts of like nasty things. Okay, that's a little bit outside of our scope. All right, so cracks and fracture are outside the scope of this discussion. All right, so away we go. Kind of our introduction here, talking about, yes, there are a lot of things that can cause warpage, shrinkage, including chemical absorption, including thermal gradients in the piece during manufacture, lots of issues. All right, we're going to focus only on the temperature changes that occur globally. So if I take this piece globally and I think about raising the entire temperature of this entire thing 50 degrees Celsius, what's going to happen? And moisture absorption being sort of a global or uniform moisture absorption, where I'm going to say this thing is now going to absorb 1 gram of water. How is that going to change that shape? Okay, so we're not going to assume that any sort of like time relationships about how long it takes to heat this thing up or how long it takes for it to absorb the moisture. We're just going to assume that it has absorbed that moisture, it has changed the temperature entirely throughout the piece, and move on from there. Okay, so with that, let's dive into actual material, and let's start speaking math language, which I'm much better at. All right, so let's define some things here. Okay, so hygrothermal strains. I'm assuming that you guys have probably seen thermal strains before, probably in your ME 2004 class, all right, which is your Mechanics of Materials 1. So let's review that quickly. That should be pretty easy. So thermal strains given by, usually we'll use like a epsilon with a T, or a T with, here I have parentheses around it. So here the thermal strain is alpha delta T, where alpha is coefficient of thermal expansion. Sometimes written as CTE. Usually units of micrometers per meter degrees Celsius. Okay, so how many micrometers does this thing expand for every meter of material if we raise it 1 degree Celsius? All right. So that's your general thermal strain. Hopefully you did problems with that like in 2004 and kind of understand that general topic. And the idea behind hygro strains is very similar. Okay, are strains caused by moisture absorption. Okay, and we denote that usually with an epsilon H. And this is going to be not alpha, but beta. And not delta T, because we don't really care about temperature change. We care about mass change. So this is beta delta M. All right, so here, beta is coefficient of moisture expansion or coefficient of moisture absorption, however you want to think about it. And here the units are a bit weird, so let's talk through it. This is going to be, again, something like micrometers, so how much my piece is expanding in terms of micrometers per meter of material. So this is like, let me do this a little bit better. Micrometers per meter of material. So I'm going to expand by a certain number of micrometers for every material I have, and not now for every degree C change that my piece goes through like I have for the thermal strains, but for every gram of water for every kilogram I absorb. All right, so it's usually meters per gram per kilogram. All right, very strange looking units. All right, so you have to sort of think about this as like a unit of how many micrometers does 1 meter of my material expand if that material weighs 1 kilogram and it has absorbed 1 gram of moisture. Okay, complicated, I know. All right, this delta M here is kind of mass change, but really it's concentration change. So let's be clear about that. So it's not necessarily a mass change in units of mass. It's a concentration change. So it's like grams per kilogram. So ergo grams per kilogram. Okay, so this will help us balance our units. So if I say that I absorb 1 gram of water per kilogram of epoxy, that would be like a delta M, right? So those a little bit more complicated. Sometimes this is presented as unitless. Which is a little bit confusing, but if you think about like meters canceling meters and like grams canceling grams, there's like a couple of factors of 1,000 there or 1,000,000 that can sort of like balance things out and kind of create sort of a unitless structure. So sometimes presented as unitless. So be aware of that. Actually, the Daniel book does present it as a unitless value. So be conscious of that. So you might see it with these units sometimes, and you might see it with no units sometimes. And if you see it with no units, you have to just understand that there is this general feel to it. And that like the meters are canceling with the meters and the grams are canceling with the grams. And there's like a factor of 1,000 that's floating around there. Okay. Okay. All right. So let's continue. And we have to talk about how this relates to lamina. All right, so this is generally for maybe an isotropic material. you would have these values of alpha and beta. For isotropic materials, they would be consistent because isotropic materials are isotropic. They absorb equally in all directions. But now we have to talk about the different coefficients in the different directions, specifically because we have composites. So complicated when we talk about composites. So here we have lamina. Hygrothermal strains. All right, so if we have the picture of our lamina in our head, this is the picture that we should have. So a lamina, remember, is one layer in a laminate. And so we have some unidirectional composite lamina that might look something like this. And remember that we have like our one direction in the direction of the fibers, two direction across the fibers, and the third direction is our Z direction. All right. So the lamina hygrothermal strains are sort of divvied up into the 1, 2, and 1, 2 directions. All right. So the thermal might look something like we have some strain that develops in the one direction, some strain that develops in the two direction, and some shear strain that develops in the 1, 2 direction. And these all have sort of that thermal moniker to them. All right, so these are the strains that develop in the piece. And here, these strains are dilatational. So what I mean by that is that absorption of moisture, or in this case, a change in temperature, will not cause any shear. Okay, so it's purely dilatational, meaning that heating it up will only cause it to expand or contract along the major directions. There will be no shear that develops. And so what that leads to is that we have a coefficient of thermal expansion in the one direction times whatever temperature change we have, and in the two direction, a coefficient of thermal expansion, delta T, and we have no shear that develops regardless of the temperature change. All right, so this is what our strains look like in the one and the two directions. And so you should be thinking in your head something that looks like this. This is my epsilon 1 from thermal, okay? And this is my epsilon 2 from thermal. All right, so there are no shear strains that develop because these strains are fully dilatational. I'll spell that out here for you. Dilatational only, gamma 1, 2 equals 0. All right, so that's your thermal. We can also have your hygro. Okay, hygro also dilatational. So you'll get some strain in the one direction, strain in the two direction, and some shear strain here with the H moniker. And here now we don't have alpha delta T, we have beta delta M. 1, beta 2, delta M. And here we have no shear strain, which develops in 1, 2. Right? So if you want to think about that in your head, again, very similar idea that here we have a strain in the one direction thermal. We can also have a strain in the one direction for hygro. Here we could have a strain in the two direction for hygro because of some moisture absorption. All right, so that's the general idea there. All right, so just like we have mechanical strains in what would be the two direction or the one direction, and mechanical shear strain, which kind of happens along 1, 2, we have typically, when we're talking about mechanical strains, some vector in 1, 2 that we can rotate to an arbitrary coordinate system. Okay, so they rotate to arbitrary coordinate system as mechanical strains do. Okay, so what I mean by that is if we have not now a 1, 2 coordinate system, but maybe we have x, y, that's terrible. We have an x, y, and we have a rotation angle here, which is theta. Okay, if we want to describe what would be the thermal strains in the x or y directions, then we can transform those strains just like you would transform mechanical strains and say that the strain in the x direction, the strain in the y direction, and the shear strain gamma xy that occur from thermal expansion going to be equal to the transformation matrix that transforms strains. So here, the appropriate transformation matrix is T star inverse, which you've all written functions to calculate, right? Right? And here multiplied by the strains which are developed in the principal coordinates. Gamma 1, 2t, or we know this is 0. All right, so these are the thermal strains that develop. Similar for if you have to transform hygro strains. All right, we know that we can sort of substitute some things in here. And we can write these a little bit differently. We just saw that this was a function of alpha and delta t, and this was a function of alpha and delta t. So we could write this in terms of alpha x, which is the coefficient of thermal expansion in some arbitrary x direction. Okay, so we can rewrite this as something like alpha x delta t, which is the thermal strain in the x direction. This will be alpha y delta t, the thermal strain in the y direction. And there will be an alpha xy delta t here, which is the thermal strain that comes from shear in the xy coordinate system, which will probably be non-zero. Okay, this here equals our T star inverse matrix, which remains. And here now we will write the thermal strains in the principal coordinates as we normally would. Alpha 1, delta t, alpha 2, delta t. And then here this is 0. All right, so here now we have a relationship which would be coefficients of thermal expansion in the x and the y directions, which are arbitrary directions, as a function of coefficients of thermal expansion of the lamina in 1 and 2 directions. Okay, so the point is, can relate alpha x, alpha y, and alpha xy to alpha 1 and alpha 2 using this transformation. So the result is the ability to write alpha x, alpha y, and alpha xy in terms of alpha 1 and alpha 2. And here I'm just going to write it in terms of m and n, which are your sines and cosine directions. Okay, so here we have alpha 1 m squared plus alpha 2 n squared. Okay, where m squared and m squared are coming from the transformation matrix T star. Alpha y, here's just going to be alpha 1 n squared plus alpha 2 m squared, and then alpha xy is here 2mn times alpha 1 minus alpha 2. Okay, so it's this strange coefficient of thermal expansion for shear if you're sort of in an off-axis coordinate system. All right, we can go through a similar exercise for beta. And we can write like a moisture absorption coefficient in x, a moisture absorption coefficient in y, and a moisture absorption coefficient xy. And so here that will be something like beta x. It's going to look very similar. Is beta 1 m squared. Okay, remember m is this cosine theta plus beta 2 n squared. Beta y is beta 1 n squared plus beta 2 n squared. And finally, beta xy is 2mn beta 1 minus beta 2. All right. So this is your Hygro expansion coefficients. All right, where m is cosine theta, n is sine theta. All right, so this is where we'll leave it today. We'll talk about next time how we define what is like alpha 1, alpha 2, given constituent properties of the fiber in the matrix that make up that lamina. Okay, so that's it for today. I'll hang out for a couple minutes if people have questions in the chat. Otherwise, thanks for coming.